So let's just compare linked lists and lists for a second. Or sorry, linked lists and array lists for a second. We don't really need a drawing to do this. We mentioned that array lists, they're kind of terrible at adding to the front, because adding to the very first item in an array list is this is an O of n operation, and then we're doing this O of n operation 10,000 times. So if I do it, well, it's actually going to take longer than that 10, because this is O of n being performed once for everything, so that's actually more of O of n squared. So that takes a while. It's still going to go, it's still going. It's going to take forever, right? So if I subtract this down to right, and now if I do this, if I double the size, this should take 4 times as long. And remember, we're adding here to index 0. We're adding to index 0 of an array list. Adding to index 0 is O of n time in an array list. It takes linear time because you have to shift n items over. So inserting it to the array list or into the front of an array list is really expensive. And we just did it O of n times there. So it is an O of n operation O of n times, which means it's O of n squared, right? O of n inside of for loop that runs n times, n being the number of items we're adding. So that's why we were getting this O of n squared time. But for a linked list, again here I'm using my linked list as opposed to Java's, just to show that it's perfectly fine. It runs beautifully because adding to the front of a list is a constant time operation, right? So if you need to review, go back to the very first video we saw. So, but remember, adding to the end of an array list was the only time we'd see constant time for adding, because we'd never have to move anything over, although there was the possibility that we'd have to reallocate. But for a linked list, let's take a look at these linked lists, specifically the doubly linked list, because Java probably does it that way. So adding. So adding to the very first node, so sorry, this is a constant time check. Adding the very first node, setting 2 pointers, so that takes constant time. Adding a node to index 0. This changes a memory location, this stores a memory location, this stores a memory location. That's 3 copies of memory locations just moving around, so this takes constant time. Same with adding to the end. It's a constant time operation. So adding to the beginning or end of a linked list, so long as it's keeping track of both the head and the tail, constant time operations, because all we're doing is manipulating these references. All we're doing is changing what values are stored in those variables. There's no loops involved. There's no seeking involved. However, get node, if there's a call that involves get node, that's suddenly going to up the time to O of n, because even though we have 4 constant time operations over here, get node will look for, let's see, this has the whole seeking thing where it runs n times, where n is the index we need to get. So you might see online on like Big O cheat sheet that like adding to a linked list is always constant time. It's not, or adding to the middle is constant time. Yeah, it's constant time if you have the reference to where you want to add, but most of the time you have to search for where you need to add it. Right? So array list, adding to the middle, we have to shift stuff over. Linked list, we have to look for the location. Roughly the same, that takes roughly the same amount of time to do. So other things, same with remove. All these operations are constant time except for removing something in the middle. Get and set, on the other hand, these are pretty terrible at. Getting an item in the array list requires us to use get node. Sorry, getting an item in the linked list requires us to use get node. Same with set, requires us to do an O of n operation. So these are slow operations. Unless, of course, you're going for the first or last, but that's, that's just returning head or tail, so not really too exciting there. Size is still a constant time operation. But, so linked lists are great if you want to add remove from the beginnings and ends a whole lot and then iterate through it. Well, we can't really iterate through a linked list the way we'd like to iterate through anything like an array list. That would actually be quite frustrating. Let's go ahead and take a look. Let's change this to a doubly linked list so that doesn't take too much time to add. Doubly linked list, because our original linked list wasn't keeping track of the tail, so adding to the end would have taken O of n time. So, but the only reason I didn't do a tail for the linked list was to keep the complexity down. There's already enough mental space going on there. So, here we go. So adding there, and now for int I is equal to 0, I is less than linked list dot size I plus plus get, or linked list dot get the ith item in the list. And we're just not going to do anything with it. We're just going to get it. Now, it was taking 9 milliseconds before, but now look at this. This is terrible. This is a terrible runtime. Why? Because the get op, we're performing an O of n operation n times. It's horrendous. On the other hand, if this was for an array list, array lists have no problem doing that because the get operations are all constant time. So, how do you properly iterate through a linked list? Not like this, because you'll have to use the get method a whole lot, and that turns iterating over the list into an n squared operation. It turns into a nightmare. An n operation performed n times. So, how is the best way to do it? Well, let's go ahead and change again this linked list to what Java has. Okay, and import java.util.linked list over here. That will just say that I want to use this linked list rather than the one that's stored in there. In this case, we want to use the for each loop. Now, I couldn't use the for each loop in my I can't use a for each loop right now because I'll show you. For each item in linked list, in linked list gives me an error right here because it says linked list is not applicable for this. I need instead to be using something that is iterable, that implements an iterable interface. And that means that it produces an iterator. In the circular linked list I'll give you, I've already got an iterator in case you need to use a for each loop, which I highly recommend you do. Java.util. Let's go ahead and see this. See, it's perfectly fine now. Oh, and that should be item. Integer. I. Right, so this iterates through just fine. And what the iterator will do is that, let's go ahead and take a look at linked list. Or let's look at the source code for linked list. Right, list dequeue. I think lit is a collection, and collections are iterable, as you can see. So iterables just have a function that return an iterator, which is an interface that just lets you go through and perform a for each loop. It's just the way Java does some things. It's weird. But if I do, for instance, iterator of integers, it's an iterator that goes over that iterates over integers. Iter is equal to linked list dot list iterator, or I can just go iterator over here. Now, what I could do is essentially a different kind of loop that effectively does the same thing as the first one. While iter dot has next, in other words, while there's still stuff to iterate over, LinkedList dot sout iter dot next. That's really what it does. It just simply says, while there's stuff to print out, we're going to print it out. And so it iterates this. And so the for loop is essentially doing this, just a bit nicer. Suffice to say, this is the way you want to iterate over a linked list. So linked lists are great if you don't care about the index, or if you do care about the index, the only index you care about is the last one and the beginning one. Otherwise, use an array list. Linked lists are great when you're repeatedly adding stuff to it and you just got to go through it sequentially all at once. That's what linked lists are good for. So they've got advantages and disadvantages. And knowing how to use them is part of the key to mastering programming.